Welcome to part 3 of my lecture series on relaxation in CFD. This is the final part of the lecture series, and I'm going to be showing you how steady-state solvers that use relaxation are actually related to pseudo-transient and full transient simulations. This talk is going to completely change the way that you look at steady-state solvers and view their results, and you're also going to learn lots of other intricate details as well. For example, why it's so difficult to actually choose an optimum value for the relaxation factors, and why steady-state solvers that use relaxation aren't often the most efficient methods of getting a steady-state solution. I'm really excited to bring you this talk. I know you're going to learn a lot from it. Let's jump into the talk. So I'm going to start this talk off by actually making some observations of a CFD simulation. And then based on those observations, we're going to carry through some mathematics and then finish off with some theory, which is going to help you understand relaxation and steady-state solvers. And the observations I'm going to make are just of the simple case of the flow over a backward-facing step, which you can see on the slide here. So we just have an inlet where flow passes in from the inlet there, and then what happens is the flow encounters a sharp corner. And of course the flow separates on the corner and we end up with this region of recirculating flow, and then the flow eventually mixes out and passes on to the outlet, which is at the right end of this CFD domain. And of course, to simulate this problem accurately, we would at least need to use an unsteady solver, and for a certain level of accuracy we might even need to use large eddy simulation. But for the observations here, I'm just going to be looking at the solution with a steady state solver and actually just looking at the solution and how it develops as we proceed iteration by iteration through the solver. And the observations are really useful, and they're going to help us to understand relaxation and how it works in CFD. So what I've got on the slides now are just a series of contour plots going from top to bottom, and the top image is just the velocity field after 0 iterations. So this is the initial condition. Everything starts with 0 velocity, and we're going to be applying the velocity at the inlet there. And there's going to be a step change once we move through the iterations. And then moving down, the second image, we've got the solution after 20 iterations, and the red regions indicating fast moving flow from left to right, and the blue regions indicating flow moving from right to left. So we've got flow going backwards there. And straight away the flow solution starts to look fairly similar to what we would expect the final solution to look like, and clearly this recirculation region isn't properly resolved yet. We've only run 20 iterations. Now if we move to 40 iterations, we can actually just start to look at the flow field and observe how it develops as we go through the steady state solver. And you can do a similar thing with your simulations as well. If you're running a steady state solution, try saving the solution after a few iterations and then a few more iterations, and just look and observe how does that flow field evolve as you carry out iterations of the solver. And the reason I chose this case to look at, the backward-facing step flow, is because there are some fairly obvious flow features which you can look at as they evolve with the solver. And you can see there's this region of high velocity flow on the top and low velocity flow on the bottom, and as we move from 60 iterations to 80 to 100, we can see that this region of flow is propagating through the domain. It's moving from the inlet to the outlet of the solution domain, and that's fairly easy to identify with this case. Now, if you ran a more complicated case, the flow may be more difficult to observe, and you could look at it every single iteration, but the key observation here is that it looks like the flow is evolving in a particular manner as we advance through the iterations. And more importantly, this evolution of the solution actually looks similar to what we might expect if we carried out the simulation with a transient approach. So the development of the steady state solution looks like what we might expect a transient solution to look like as the flow develops. It's being pushed and it's moving from left to right all the way through the solution domain. And that's the key observation that I wanted to make to start off this talk, is that the development of the steady state solution when we apply relaxation looks similar to a transient simulation. Obviously it's not going to be the same, it's not going to be exactly the same, but it looks similar, and this tells us that perhaps the two are related. Perhaps the steady state solution with relaxation is actually linked to a transient simulation in some way. Perhaps there's some way that the two are related, and that's going to be the focus of this talk. So now that we've made the observation, let's actually go and dig into the maths and see if we can work out if this relationship exists and what it looks like. And once again, I'm going to use the same example that we used in part 1 and part 2 of steady state heat conduction in a bar with 4 elements solved with an iterative solver. And once again, we could assemble the matrix equation for this flow scenario by starting by applying conservation of energy to a particular cell. And for example, for cell 2, we take the heat flux through the left face of cell 2, that's going to be Ka delta T over delta X. The heat flux out of the right face of the cell, Ka delta T over delta X again, and then the heat source in that particular element, and of course with conservation of energy, heat flux coming in, heat flux coming out, and the source in the bar must balance to give 0 under steady state conditions. When this simulation has converged with an iterative solver, that equation will be satisfied for cell number 2, and we get a linear temperature profile which satisfies that equation. And the same as we've done before for part 1 and part 2, we can just expand that equation and rearrange the terms to highlight terms that are common to T1, T2, T3 and T4. And we can do that and then introduce these coefficients A1, A21, A22, A23, A24 to represent these Ka over delta X terms that are multiplied by each of the temperatures. And that makes it easier for us to assemble matrix equations. And we can use the same trick that we used in part 2, where we're just going to isolate that diagonal term. So the term involving T2, which has got the Ka over delta X and Ka over delta X there. I'm going to call that A22 multiplied by T2, because we're looking at cell number 2, and then collecting all of the other temperature terms together, so the T1, the T3, the T4, and then combining those together with the summation notation, just for conciseness, in the same way that we did for part 2. And we can generalize this equation by replacing the cell 2 with cell P, where P is a general cell in a CFD mesh. And so this is the equation for the steady state conservation of energy for a particular cell in the CFD mesh when the steady state solution has converged. But before that, before the equation has converged, this conservation of energy won't be satisfied, and there'll be some imbalance or some residual energy flux, which we've seen in previous talks. There'll be some additional terms, some additional error or imbalance. And I've just added this onto the left-hand side and called it imbalance. And what we saw from looking at that backward-facing step flow earlier in the talk is that we've seen that the development of the solution with this steady-state solver looks similar to a transient simulation. And so what we're going to do is just take this unknown imbalance that we know is there and just replace this with a transient term. And we're going to do that to carry out an investigation to see, is that a reasonable thing to do? Is the imbalance related to this transient term? And what does it mean? Is the intuition that we have from those observations, is that correct, or is it in fact not correct? And do we need to do something different? So what form does this transient term take? And what I want you to do is just consider the simple example of an element of that solid bar. So this could be cell 1, cell 2, cell 3, cell 4, or any cell in the bar. And that particular cell, in this case, I've drawn it as a cube, but it could have any shape. It could take the shape of any cell in a CFD mesh. And we've got a solid bar, so this cell is going to have a certain mass, it's going to have a certain volume, which we can get from the shape of the cell and its density. And then depending on the material that the cell is constructed from, it also has a specific heat capacity, Cp. And what's going to happen is that, of course, if we add thermal energy to this cell, if we added it from a heat source, or if there was some additional heat in there from the imbalance in the energy equation, that additional thermal energy would cause the temperature of that element to rise. So as we add thermal energy, the temperature rises. And of course, the temperature rise that we get depends on the mass of the cell and its specific heat capacity. So cells or elements in general with higher specific heat capacity, material with high specific heat capacity, if you apply a given amount of energy, because its heat capacity is high, its temperature rise will be low. So this is what would happen if we add thermal energy to a particular bar, an element in the mesh. And of course, that treatment only applies for solid cells, the MCP delta T. If this was an element of mesh with a gaseous system, then adding heat to this particular region of gas would increase its pressure as well as increasing its temperature. And so if we were considering a general fluid system, then we would actually write this in terms of a change in enthalpy rather than a change in temperature. So we could account for the change in the pressure as well as the temperature. But for simplicity in this talk, I'm only just going to be looking at the solid bar and the solid elements, because this equation is more familiar to people and it's easier to develop the understanding that we need for this transient variation. So we've got this Q is MCP delta T, so the additional thermal energy in that cell in the bar mesh is going to raise its temperature. And the thing to notice is that in our equation for conservation of energy, all of the terms have units of thermal power, so this watts or joules per second. And so what we actually need to do to derive this transient term properly and apply it is we need to rewrite the thermal energy as the thermal power multiplied by some increment in time. So power times an increment in time will give the MCP times the increment in temperature that results from that additional thermal energy. And if we just divide both sides through by the increment in time and then take the limit as that time step reduces down to 0, we end up with this additional equation, equation 12. So the power will be mass of the cell times its specific heat capacity times the rate of change of temperature with time. And the final simplification we're going to make is just replacing the cell mass by its density multiplied by its volume. And this is the additional term that we're going to add to our energy equation. And remember, we have that imbalance term which will exist until the simulation converges, and we're saying we think that imbalance may have similar behavior to a transient. And so instead of writing imbalance, we're going to add this transient term instead to the left-hand side. And so this is what our steady state energy equation will look like for the solid bar before we reach convergence when we're solving with relaxation. And so just to summarize here, it's very important to remember that this is an artificial transient term. We're not solving this equation with a transient solver, we're still using a steady state solver, but we've added this artificial term just to provide understanding. And so it's not a true transient, and I'm going to discuss that in more detail and actually the reasons why it's not a true transient in the next lecture series, which I'm going to do on pseudo-transients and true transients. And for this reason, the artificial transient term that we've just added here is sometimes referred to as a pseudo-transient, just to be absolutely clear that it's like a transient, but it isn't a transient. And if you're interested in more detail as to why that is the case, definitely stay tuned and watch my next lecture series on pseudo-transients, because I go into that in detail and you'll get a lot more understanding of it. So now to make some progress, remember we need to go back to our investigation. We're trying to understand how does that steady state solution evolve before it's converged. And what we're going to do is just replace that derivative, rate of change of temperature with time, with a first order implicit Euler scheme. And so to understand how that works just from a graph, you want the gradient, so rate of change of temperature with time. And what we're doing is drawing a local tangent to there and taking the change in temperature divided by the change in time. Of course, this is a first order scheme, but for us and the understanding that we need, this is perfectly sufficient for the gradient here. We don't need any higher accuracy. So let's replace that temperature gradient with the first order Euler scheme. We do that to get from equation 16 to equation 17. And now what we're going to do is just rearrange the terms. So I'm going to collect the terms that are multiplied by TP together, and then I'm going to move the terms that involve TP old and put them on the other side of the equation. And when I do that, I arrive at equation 18. And this is a new equation. We haven't come across this one before, but when we look at this in a bit more detail, we see that it has some interesting similarities with the equation for implicit relaxation that we looked at in the previous talk. And the easiest way to do that and to start understanding these differences is to just write this equation out into matrix form. And what we can see straight away is, remember that this first term, this is the diagonal coefficient, which was A22, which is multiplied by the temperature. And then everything on the right-hand side becomes a source term. So for our 4x4 matrix, this is how the matrix is going to look when we add that artificial time derivative to the left-hand side. You can see that the diagonal coefficient on the matrix was originally A11, but we've now added this extra term which depends on the cell density, its specific heat capacity, its volume, and also the time step. And we're going to be coming back to look at the time step later on in this talk. And we've also got an additional contribution to the source term. So even though these terms have some different mathematics to what we've seen before, the general effect on the matrix equation is consistent with what we saw in part 2 for the implicit relaxation. We've changed the diagonal coefficient and we've also changed the source term. So already we're starting to see that maybe this implicit relaxation method is linked in some way to the pseudo-transient approach. And just a reminder of how that matrix looked when we applied implicit relaxation from part 2. You can see that we had A11, A22, A33, A44, but we divided it by the under-relaxation parameter alpha there. And we also had this additional source term on the right-hand side. And both of these, if you recall, have the effect that because alpha is less than 1, we get an increase in the diagonal coefficient on the A matrix, and we also get a source term which increases as alpha tends to 0. And looking at this new matrix form that we've derived for the pseudo-transient approach, we can see a similar thing, that as the time step delta t gets smaller and smaller, as we reduce the time step, this fraction is going to increase, which increases the diagonal dominance of the matrix. And we get a similar thing with the source term. As delta t goes to 0 and we have a smaller and smaller time step, this source term is going to increase, which is going to slow down the calculation. So we're getting similar qualitative behavior to what we saw with implicit relaxation. But what happens if we go further, and rather than just making that qualitative comparison, what if we actually compare the terms mathematically and see how they're really linked? And if I just compare the equations side by side, on the top I've got this pseudo-transient equation that we derived in this talk, and then in equation 20 I've got the implicit relaxation formula from the previous talk. And what I'm going to do is compare or equate the coefficients here in front of TP. So I'm going to equate AP plus rho Cp Vp over delta T with AP over alpha. I'm going to equate those terms together to actually see mathematically how they're linked. And just a side note here, you could also do the same thing with the source term. You could equate the source terms together and you'd get exactly the same result. You can equate either of these, both will work, but I'm just choosing to use the diagonal coefficient here. So if I go ahead and do that and set AP plus rho CPV over delta T equals to AP over alpha, then what I do is rearrange for this time step delta T. And after I do that, I arrive at equation 22. This is a really important equation in this talk, and you can derive so much understanding from it, and that's why I've highlighted it in a box here. And the first thing that this equation tells us is that the relaxation factor alpha is related to a pseudo time step. So when we choose a value of alpha, in some way that's linked to an effective time step which would occur if we were to solve the simulation in a transient manner. So that tells us the very important result that applying relaxation, so when you change that relaxation factor in the GUI of your CFD code, this has a similar effect to advancing the solution through time with a transient solver. So steady state and transient solvers are actually linked, and I'm going to go into more detail about that specifically and the implications it has, because I imagine that at first glance this could be quite confusing, that I thought steady states and transients were very different. Well, they're actually linked. And for those of you who want the reference for this equation, you can find this exact equation in Ferziger and Peric on page 149. If you want a reference for this equation, you can grab that one there. So what's the next bit of information that we can pull out from this really important equation? Well, if we just look at the terms in the equation, then we can see that alpha is the same for every cell in the mesh. So all of the cells in the bar, we will have assigned a relaxation factor of, say, 0.7 or 0.4. So alpha is the same for every cell in the mesh. And rho CP and VP may be the same or may not be the same, depending on if the mesh is uniform or if it's non-uniform. But one thing we can say is that this coefficient AP will be different in every cell in the mesh in general. And so what that tells us, by looking at this equation, if you had a general CFD mesh, like a mesh which you may have, when you choose a relaxation factor of, say, 0.7, that's applied to all the cells in the mesh. But the result of that is that the simulation evolves with a similar effect to a transient simulation, but with a different time step in every cell in the mesh. And that's something which you may take a little while to get your head around, and so I've just put a simple diagram here on the slide to explain visually what effect this is happening. So if you had your bar and you solved this with an implicit relaxation method, and you set your relaxation factor to, say, 0.7, and then pass it through this formula, that would be equivalent to advancing a pseudo-transient solution, so almost a transient but not a true transient, but with different time steps in every cell in the mesh. And that, of course, means that some cells will reach and arrive at their final solution faster than others. And it also means that those in-between solutions, so if you save your steady state solution before it's converged at the end, because the cells have advanced at different rates towards the final solution, that intermediate solution is not physically valid. So there are some very, very interesting points which you can deduce from this pseudo-transient. And I also encourage you just to have a think about your case. If you're running a CFD simulation, just visualize the mesh that you're using at the moment and the relaxation factor that you may use, and then also think that this actually has the effect of taking all of those cells and applying a different time step to all of the cells and then advancing them all together towards the converged solution. So this also has some interesting implications for the relaxation factor that we choose. You may remember from the previous talk that I mentioned that if you reduce the value of alpha, you slow down the simulation, but you make it more stable. And often you have to use a bit of trial and error to find which value of alpha is going to give you that compromise and the best performance. And this can often be tricky to do because you would have to play around, and every single simulation is different. Some simulations having an alpha of 0.6 may be the best, and some may have 0.7 as the best. And the real reason why that's so difficult to do is because effectively what you're doing is having different time steps in every cell in the mesh. And when you change alpha, you're changing all of the time steps in all of the cells in the mesh. And naturally, this is really difficult to do because every problem will have a different optimum time step, the most efficient way to push that solution from its initial condition all the way through to the converged solution. And this is why alpha is so difficult to optimize. And Another way you can think of this is, let's say you chose a value of 0.3 for alpha, then a particular cell in your mesh may have a pseudo or effective time step that's really, really small. And so this cell would then slow down the solution, and that's why you couldn't get there really efficiently. But in a similar manner, if you made alpha really large, some of you may notice that when you increase the value of alpha, sometimes your solution diverges or starts oscillating, and that's because you've changed all of the time steps in the mesh, but one of the cells, or a few of them, may have a larger effective time step that's too large and therefore makes the simulation unstable as you try to solve it. And this is why, when you look at CFD codes, there are often a number of different relaxation factors that are provided to you by default, and these have been chosen as a compromise over many different cases, but it wouldn't be possible to have an optimum value for all CFD cases that you could possibly run, because of course the effective time step that would be best is also different for every single CFD case that you run. And so what does this tell us about the overall algorithm and approach that we're currently using to solve steady-state CFD problems? Well, it tells us that actually our approach isn't very good, because we're choosing different values of alpha for all of our equations and then using some kind of trial and improvement approach to try and optimize the value of alpha for each of those equations, which is in effect optimizing pseudo time steps, which are different in every cell in the mesh. And this is really difficult to do and can be time consuming. So a better question would be, can we actually propose a different algorithm for solving steady state problems that would be better than this approach of relaxation factors? And the first thing to think about from this talk is, what if we took the opposite approach? So rather than having a value of alpha that's constant for all of the cells in the mesh, why don't we take the opposite approach and have all of the cells in the mesh have a constant pseudo time step, and as a result that's equivalent to having a value of alpha that varies throughout the mesh. So taking the approach that we looked at here, but what if we did it in reverse? That in theory would be a better approach, because all of the cells in the mesh would be advancing through time at the same rate, and so convergence is likely to be more uniform for all of the cells in the mesh. And it also gives us a way to just directly calculate what values of alpha we should be doing without trial and improvement. And so this is actually the basis of the pseudo-transient approach for solving steady-state CFD problems. And we really need to go into a lot more detail to fully understand the pseudo-transient approach, and that's going to be the basis of the next lecture series that I do. Is going to be all about pseudo-transients and how we choose this effective time step to then back calculate alpha. But for this talk, that really summarizes everything I wanted to talk about here for part 3 of relaxation. And the main points to take away from this talk is that when you use a steady state solver with relaxation for stabilization, the effect that this has on your CFD solution is advancing it through time in a similar approach to a transient simulation. However, the key difference is that this is in effect advancing your solution through time at different rates in all of the cells in the mesh. Some cells have a larger effective or pseudo time step, and some cells have a smaller effective pseudo time step. And this is because we've chosen a value of alpha that's constant throughout the mesh. And this also explains why the optimum value of alpha varies on a case-by-case basis, and the values of alpha that are provided as default by CFD codes are often a compromise that work reasonably well for a wide variety of cases, but aren't guaranteed to be an optimum for whatever case we happen to run. And the final point there is that when you use a pseudo-transient approach, so if you ever notice this setting in your CFD code, if you click the option for pseudo-transient for a steady state, this is still a steady state solver and a steady state solution process, but in effect what we're doing is advancing that solution through time with a different relaxation factor in all of the cells in the mesh. So that brings me to the end of my 3-part lecture series on relaxation in CFD. I'm really hoping that by the end of this lecture series, you've now got a really clear idea of what under-relaxation is in CFD, what all the different parameters mean in the CFD code, and what values you should be choosing for your simulation. Now, the next series of talks I'm going to be doing will be on the pseudo-transient approach that we started to introduce in this talk here. I'm going to be looking at that pseudo time step, how you might choose it, and also what the difference is between a pseudo-transient approach and a full transient or a true transient approach. And you're going to get a lot of understanding from this next lecture series. So if you're looking forward to that, let me know in the comments section. How did you find this lecture series? Did this clear up any doubts in your mind that you had about relaxation, and how are you feeling about the topic now? So until next time, thank you all very much for watching. I really do appreciate your continued support with the channel, and I'll see you in the next video.